Okay, great. So we're happy to have with us today, and in fact, for the week, Daniel Kunin. So Daniel is a PhD student in ICME, Institute of Computational Math and Engineering. I got that right?
Yeah.
I learned that 5 minutes ago. In Stanford, working with Surya Bengali, and Daniel has really caught our attention and my attention also in doing really interesting stuff and trying to understand the dynamics of neural network training, which I think, as we discussed just a few minutes ago, is maybe the most exciting and interesting question now in kind of understanding the most important thing happening in the world. Daniel is graduating in a few months or weeks, and will be days? No?
Weeks.
Weeks. And we'll be joining UC Berkeley as a Miller Fellow for the next couple of years.
Yeah.
Okay, so we're very happy to have Daniel with us today, and again, Daniel will be here throughout the week if you want to try to catch him.
Yeah.
Looking forward to the talk.
Okay, great. Well, thanks for having me. Yeah, I'll be here for the rest of the week, and I'm hoping that we can find some time to converse after this talk. So, yeah, I'll be introducing this is my thesis title, An Introduction to Learning Dynamics of Neural Networks, Conservation Laws, Implicit Biases, and Feature Learning. And hopefully by the end of the talk, or maybe in the middle, this GIF will make a little bit more sense. Let's see, I think I gotta turn this back on and off. All right, we'll just use this. Okay, so
there should be another one.
it's okay. Okay, so yeah, I kind of view my work as trying to understand the mathematical principles underlying deep learning, in particular the dynamics of deep learning. And when I think about this question of trying to understand deep learning, I really think it comes down to understanding this interaction of three components that make a deep learning system. We have these deep nonlinear architectures, we have high-dimensional natural data sets, and then we have this stochastic gradient-based optimization. And deep learning is really about the interaction of these three components. It's not just one of the components, and we can't study them independently of each other. And from this, I've seen kind of two perspectives in the literature and perspectives that I've taken in my own research. One I would call kind of this implicit bias perspective. So the idea is that it's the optimization process has some bias towards simple solutions like maximum margin properties, minimum norm, low rank, sparsity. And here I think it's really about the interaction of the architecture with the optimization. And sometimes the data is kind of left on the side. Maybe we make some simplifying assumptions like it's linearly separable or something along these lines, but it's not necessarily the focus of the analysis. And then there's this other perspective, which I think is maybe a more empirical perspective, which is that really the reason deep learning works is because they have some ability to learn and compose task-relevant features from data. So this has been, for as long as we've had successful models, we've been observing these ideas. Like, for example, the observation that there are edge detectors in the first layer weights of CNN. So that when we have word embeddings, which is the basis of all NLP, that you add king and queen and you get man and woman. So there's these meaningful word embeddings. Or more recently, there's a large work around mechanistic interpretability, finding interesting features in neural networks like that. When trained on modular addition, they learn to use a Fourier basis, so like why a Fourier basis. So I think these perspectives are, I guess I should mention that this feature learning perspective often ignores the optimization. So in this case, feature learning is really about, at the end of training, can we observe kind of features from the data in these trained neural networks? And so today, my work has kind of bridged both of these fields. Mostly focused during my PhD on the implicit biases, in particular the effects of finite learning rates and stochastic gradients. But today I want to talk about more recent work on kind of feature learning perspective. So I'll mostly be touching on this work, and my hope is to touch on this work as well, which is a preprint, and we'll see how far we get. Okay, so the questions that are going to focus this talk around are, what conditions enable feature learning? So when and why does feature learning emerge? And then the second question, which is the second part of the talk, will be what mechanisms are actually driving feature learning? What features are the networks learning and how? Okay, so to get into the first question, I guess we should start with, well, what is a feature? You see this across, people use the word feature in neuroscience and mechanistic interpretability in deep learning theory. And they kind of all, at the end of the day, have their own maybe definition with varying degrees of formality. So maybe I'll give a somewhat vague definition, but a feature is just some representation of the data, some function of the data that the model will use to make a prediction. So you could think of this as the last layer activations. In this talk, we'll often be thinking about these as the MTK features, so the Jacobian of the function, evaluated at some data point. To give some context, let's give an example of this. Imagine we were given this problem of trying to separate or classify the red circles from the blue circles. And these points are given as XY coordinates with some label, and we want to learn a classifier. Well, we could just look at the representation of this problem in XY space, or we might realize that if we transform our data and look at, essentially x squared plus y squared, and we look at that feature, now all of a sudden this data set becomes separable. And so really, when we talk about feature learning, there's this kind of notion of like, what are the right features? And in traditional ML, this really relied on handcrafted feature selection. So in this problem, of course, it's a very simple problem, and we know, okay, this is really, all I really need to know is x squared plus y squared. But the amazing thing about neural networks is that by just giving them data and training and compute, they seem to learn to the right features. So the question around feature learning is exactly how do they learn these features? Okay, so if we want to understand when does feature learning happen, a good place to start is probably when doesn't it happen. So we'll start there. So when doesn't feature learning happen is actually a very well-studied regime of training in neural networks. And this is basically when a network becomes linear in parameter space. So this very famous paper now in 2018 introduced this object called the neural tangent kernel. And in the paper, they showed that if I take kind of an arbitrary network, and there's some conditions, but if I take this network under a certain parameterization and I scale the width of the hidden layers of this network, as I scale the width towards infinity, this network becomes more and more linear in parameter space. And by linear, I mean that the function looks closer and closer to its linear approximation. And here, the feature map is this Jacobian, these neural tangent kernel. This is the neural tangent kernel feature map, let's say. Yeah.
Can I ask a somewhat, maybe annoying question you can choose to ignore?
Yeah.
But how do you define a feature here? I mean, when you're saying here that feature learning doesn't happen,
Yeah.
what is the feature?
So
because you're learning the feature. I mean, or rather, how do you distinguish a feature? Is just the label is also valid.
So what's happening here is this in this case, this Jacobian of the function are the features. It's this function of my data.
Well, why do you call them the features? I guess it's
Well,
like what is a feature?
Okay, back to the vague definition. A feature is any function of the data that the model is going to use for prediction. In this case, the model becomes linear in parameter space, so this theta here is changing. But this function this is kind of it's doing linear regression with this representation of the data. And when I say there's no feature learning happening, what's happening is that this vector is not changing through training.
But theta times that vector is changing.
Yeah, so the prediction is certainly changing.
Why is not that a feature?
Okay, so yeah, then you could argue
No, I'm trying to
that,
understand whether you have a
Yeah. I mean, then in which case, if we're just studying linear regression, when we initialize linear regression somewhere, in the beginning you predict nothing, you don't know anything. Eventually, we hope that it learns something. So in that case, it has to have. If your feature is your prediction, then you have to have learned. You have to have feature learning.
Right.
But really, we want to disentangle this point where there is a way to fit the data in a way where you are learning some sort of meaningful representation of the data, or there's a way to fit the data by just kind of overfitting to it, just memorizing it. And so in this case, I'm taking one step back and saying, okay, maybe, yeah.
But you're not memorizing here. You're
All right.
learning it. Okay, so
I'm gonna move on.
Okay.
But I think this, I'm gonna move on.
Okay.
All right. So but this paper provides an interesting point. They're saying, look, we want to understand the interaction of these complex systems. Here's a regime where we can understand all of that interaction.
No, just to clarify, just to know the story, just just with the word feature and like if we're
I think
doing
honestly
something
it's a
here,
really good question. Like in the sense, well, maybe. I think it's a good question to define it's hard to define a feature. It really is, because it gets back to this thing is like this isn't a really great definition of feature because it means nothing to me. At the end of the day, I want like a human interpretable feature, right? When we say we want to understand deep learning, kind of what we're asking is we want to understand how, in a way that we, not just, in a binary sense of code, but like what aspects of the data that are humanly interpretable to us is it picking up on? So, having good definitions of features is actually, I don't know if I think it is quite difficult. So in this case, we're going to say it's the Jacobian of the function, and feature learning is whether or not that Jacobian is changing or not. That's what I'm going to say. Okay, so this paper that came a year after actually introduced an interesting point, which was really the scaling the width might not have been the important aspect of this regime, but it had to do with the initialization variance, and that if I could take a finite width network, and there's some other conditions, but if I took this finite width network and I initialize all my parameters as random Gaussians, but I scaled the variance of those random Gaussian initializations, I could move it into a similar regime where the network would never leave essentially its first order approximation in parameter space, meaning the network was, this feature map was not changing through training, but its predictions were. Okay, so let's try to kind of quantify that more precisely in an experiment. So inspired by this paper. So we're gonna look at, we're gonna try to train a wide 2-layer student network. So this is my network, it takes in input in R2, outputs a scalar, and its hidden layers use a ReLU nonlinearity. So this is the form of the network. And it's gonna be trained on data generated from a narrow 2-layer teacher network of the same kind of functional form. So this teacher network will generate data, will then train the student from that data. And in this case, the right features, quote unquote, are whether or not the student neurons kind of align to the teacher, whether or not essentially the student realizes that I don't need 100 hidden neurons to fit this data, I only need 3, because that's where it came from the data. And we're gonna visualize some of this through training, so just to be clear about my visual language here. My data is in R2, and I'm going to plot the 3 teacher neurons as just the directions are these dotted lines, where the color represents the sign. So again, each neuron here, I have 3, 1, 2, 3. My hand's a little shaky apparently. There's a vector in R2 that goes to this hidden neuron, that represents the direction, and then there's kind of a scalar which is going to represent the sign, the color. Similarly, the student neurons are also going to be points now in this map, and also colored by the sign of their second coordinate. And I'm going to initialize them all at the same, on some circle of the same radius. So they all have the same initialization scale. It's a loosely approximating what Shazat said with this random Gaussian. In this case, just finite, they're random directions, but all have the same radius. Yeah.
So what exactly is the objective of the student?
So the objective is going to, it's mean squared error, trying to fit the labels, it gets access to the x's.
Labels, not the logits.
The labels are actually, it's regression. So in this case, it's just mean squared error.
So I may be misremembering, but in general, you can have a student network in a typical computing settings, which actually does better than the teacher, which means that its neurons are necessarily not going to be exactly the subset.
So in this case, better.
Different setting?
This can't be better than the teacher because it is literally, the data is coming from the teacher in this case. I mean, you may be better if it.
Only from the teacher.
Yeah, the data, there's no noise.
But okay, I think the traditional one, you have a combination of the ground truth and the teacher. Here, you just have the teacher.
Let's just say, this is the setup. Just the teacher, I have inputs.
I see.
Teacher generates outputs, student gets the inputs, tries to learn the outputs.
Right.
So let's visualize this. So what I'm gonna do now is I'm gonna train this network on that task at differing initialization scales. So different radii for this initialization circle. Same data though. And we'll just watch this run for a second. All right, so I should also mention, okay, so this red line here corresponds to this plot here. The green line corresponds to this. Maybe I should have done some sort of color matching. But one thing that we quickly see is that at the very large initialization scales, we saw very little movement in the parameters of the student. And yet, while there was very little movement in the parameters, there was a quick drop in the loss. It quickly learned to interpolate this data. Meanwhile, at small scale initializations, the student actually at the end we see has some striking alignment towards the teacher neurons, but it started with a very long plateau where we saw very little change in the performance. And so Yeah, maybe let's just watch that again, mostly just because this took a long time to make, so it's worth seeing it twice. So yeah, you can kind of see this happening here. There was almost very little movement at first, but then these neurons kind of exploded out in very specific directions. So there was some sort of alignment that occurred before there was fitting. And during that process, that was kind of corresponding to this plateau. And then once it kind of fit, there was this drop. Meanwhile, at large-scale initializations, there was very little movement. So yeah, this kind of confirms this idea that we saw in Shazat, that the parameters basically didn't move very much in this setting here, and yet they were able to fit the data very quickly. Even at small-scale initialization, I can get very similar behavior by just kind of changing the relative scale between the parameters, so A and W versus W and A. In this case, I'm making A's, I'm keeping the product the same, but I'm making the parameter, second layer much larger than the first, or vice versa. And we see very striking different behavior in the way in which they learn the problem. Okay, so the goal is to kind of try to understand this a little bit more in this first talk, but before we get there, let's just set some basic background of the way I view this problem. So in general, I think a key idea in deep learning is that when we want to understand dynamics, we really need to understand dynamics in different spaces. So we have essentially this high-dimensional parameter space, in this case the parameters of all the neurons. And we initialize at some point in this high-dimensional parameter space. And then the functional form of our function kind of maps those parameters to a point in the space of all possible functions that architecture can represent. Then, given some data, that maps with the loss to some performance. The gradient of the loss with respect to the function, maybe we call that the residual, maps that back, a gradient back into function space. And again, that the Jacobian of the function back to our parameters creates a gradient in parameter space. We then update and we move, let's say, under gradient flow. So we have dynamics occurring in this parameter space, which map to dynamics in the space of functions, and finally in our performance. And the key idea is that between all of these different spaces, this object called the neural tangent kernel, which is just the kernel associated with that Jacobian of our function, is the kind of map between these two or three spaces. And that kind of intuitively, one way to think about what the neural tangent kernel says it quantifies how one gradient step with one data point affects the evolution of the network's output evaluated at another data point. And so if there is a feature learning occurring, this kind of influence should be changing through training. There's lots of different ways you can look at that and see that, but one easy way is, again, back to my definition of a feature, it's going to be that Jacobian of our function. If that Jacobian is changing, this feature map is changing. And so when does feature learning emerge? It's not binary. It's not like you either have it or don't have it. It really is a spectrum of the degree to feature learning, where in one regime we might call this kind of kernel learning or lazy learning, and that's when the NTK is not evolving. That kernel is not evolving. And the other extreme, we have feature learning or sometimes rich learning, and that's when the NTK is evolving. And it really then becomes a question of how much evolution are we talking about is the degree of feature learning. But we also see that it's associated with kind of large-scale initializations versus small-scale initializations. We saw that in the curves. In the loss curves, we see kind of exponential loss curves versus sigmoidal loss curves, kind of plateaus followed by drops. And so, yeah, maybe answering the first question, feature learning occurs when the NTK evolves. But now we're going to try to kind of understand all these other aspects that are associated with feature learning. Yeah.
Could you just clarify large scale versus small scale?
Yeah, so in the experiment I was showing earlier, it was the radius of the initialization, but in general, it's going to be the variance of my random Gaussian initialization. So large scale just means very high variance, and small scale means low variance. One way to think about this that we'll eventually get to maybe in the second part of the talk is small scale initializations is when I take my parameters and I'm moving them closer to the origin. So in some sense, if I put all my parameters at the origin, the model, that would be a saddle point of the loss. The model won't leave the origin. But as I get closer to the origin, we're going to see more and more of this stepwise behavior and kind of a large degree of feature learning. Yeah.
How did the fact that in the large initialization we didn't see much movement, how does that tell us that the NTK is not changing?
Yeah, you would actually have to look at the parameterization, but this is a good question. We're going to go into a specific example where we'll see that. Yeah. So this kind of is actually to your question, why at are small scale initializations, or you could just converse, y at large scale initializations, do we see sigmoidal loss or exponential loss and change in NDK versus no change in the NDK? So this is the next part of the talk, is we're going to consider a very simple setting, a minimal model, a single linear neuron, and we're going to kind of deeply try to understand everything about the dynamics in this setting. So this hopefully will give some intuition, yeah. But maybe actually just another degree of intuition. The NTK comes from a first order approximation to your network in parameter space. So if your parameters don't move far, they don't really leave the first order approximation to the function. That's another way of thinking about it. Okay, so this work is based off of this part of the talk is going to be based off two works. This paper that Natty was a part of, and it I think some other members of this paper were from TTIC, and then this one, which is published last year. Okay, so in this paper, we kind of expand upon the analysis in this section. But before we get there, let's just give a quick kind of high-level overview about linear networks. Sometimes people ask this question, like, why study a linear network? Aren't all linear networks the same? Well, it's true that linear networks are linear in the input, but non-linear in the parameters. So there's a long, long line of literature studying the dynamics of linear networks because they really have quite interesting non-linear dynamics that seem to echo what we see in realistic networks. And there's one thing, though, that all of these networks, all of these analyses share, and that is that linear networks have this symmetry where I can take the first layer, for example, and I can multiply it by some invertible matrix, G, and I can take the second layer and multiply it by the inverse of that matrix, G inverse, and nothing changed in the map. So you have this kind of rescale symmetry in the parameterization that leads to lots of interesting properties. For one, it means that the minima is not unique. Rather, there's these kind of smooth manifolds of minima. If I had one solution, I can find another by just kind of using that symmetry there. And second, there's this structure in the gradients with between the layers. So you have this interesting kind of relationship between the gradients of A and of the second layer and the gradients of W. And this structure here immediately implies that actually there's this conserved quantity through the training dynamics. So this difference in gram matrices is actually conserved through training. So yeah, there's a long line of literature studying linear networks, but at the end of the day, almost all of the analyses use some aspect of this, a conserved quantity. And I do want to just quickly highlight that the existence of these conserved quantities under gradient flow isn't unique to linear networks. In fact, whenever you can find these kind of continuous symmetries in a neural network's parameterization, you can find conserved quantities under gradient flow. So for example, the weights before softmax have a translational symmetry or translational invariance. There's a scale symmetry in the weights before normalization layers. Again, kind of this rescale symmetry between layers when we're talking about linear or piecewise linear networks. And really, actually, there's a kind of a nice connection if you're coming from more of a physics background, which is that this is really kind of deeply connected to Noether's theorem, where if you have symmetry in the parameterization, continuous symmetries kind of maps to conserved quantities in the dynamics.
Question.
Yeah.
So, I guess the difference here is that the infinitesimal action, like the differential equation you get from like playing with the symmetry by like observing infinitesimally, doesn't always give you an integrable system.
Yeah.
Right.
Yeah.
So that's kind of like the only non-trivial part of Noether's theorem, like the proof that's always integrable.
Yeah.
But you do get the differential equation, but how can you always get a conservation quantity from this symmetry?
No, there is
Okay.
satisfying mild assumption, asterisk. Yeah, so not every continuous symmetry, but many of the ones that we actually care about or observe in neural networks will lead to these conserved quantities under gradient flow, and then in fact when you introduce stochasticity and all these other things, they're not.
But the analysis seems like ad hoc, like we don't know like when does this symmetry leads to or like continuous symmetry leads to a conservation quantity or when not. It's just like always case by case study. Do you have like deeper
A more
insight?
general? No, I never was able to fully understand. This condition is essentially the condition needed to make the analysis work.
Yeah.
I never understood like exactly a good, which is basically the condition needed to make it integrable. Yeah.
Is it some kind of commuting condition there? Is that?
It very well, I don't remember,
Because it
I don't
seems-
remember, but it very well might be, yeah. But I think the only thing I was trying to highlight here is just that this idea of like using conserved quantities that we see is gonna be paramount to our analysis of that single linear neuron. It's actually something that kind of occurs throughout deep learning as well. And there's this kind of nice, interesting connection to physics. I mean, I actually, from taking kind of a step back, I really think that and I'm sure I'm not the only one in the room that thinks this, that physics is a really nice analogy to understanding learning. It's, learning in some sense is a movement problem. Physics is all about mechanics and movement. And so there's lots of tools from physics that have direct analogy in the study of deep learning. Okay, so back to our minimal model. So let's just first write out the gradient flow dynamics for our parameters, A and W. So again, we're training this model on mean squared error, and so it's just trained on a linear regression task with some data generated X and Y. And the dynamics for A can be written like this, and dynamics for W like this. And again, the key thing we're going to be looking at is how does this initialization change the dynamics and the solution that it learns. So right off the bat, as we should expect, there should be a conserved quantity. In this case, it's the difference between the norm of A, or this squared value of A, and the norm of W. So this conserved quantity delta is determined at initialization, and it constrains the dynamics of our model to keep that quantity conserved through training. So in this kind of visualization, I have W as a vector, W1 and W2, A is a scalar, and so this conserved quantity can be mapped to basically different hyperboloids, which are constraining the trajectory. If in the case where delta started negative, it's like this one-sheeted hyperboloid. When delta is 0, it's this double cone, and when delta is greater than 0, it's this two-sheeted hyperboloid.
Can you in delta equals 0? Can you go between them?
So no, in fact, you can't.
Okay.
Yeah. So let's just give some more visual, labels to what we're looking at. So I'm plotting the surface here is the conserved quantity, meaning the dynamics can never leave that surface. Wherever surface they start on, they can't leave. The color on the surface is representing the loss projected on that surface, or just the loss on that surface. What about, and the dynamics are essentially, they start at these points here and they move to these points here. So just to be clear, what are these kind of red and gray hyperbolas here? These kind of one-dimensional hyperbolas. The red one is the space of solutions. So the place where A times W is the OLS solution. And the gray one is the space of equivalent initializations. Meaning I start somewhere on this gray hyperbola and I move along the surface of this blue of my conserved quantity, trying to reach the red hyperbola. These points are intersecting uniquely here. There's a couple other things though that we'll find is that there are saddle points of our loss, right, for example, in the double cone, right at that intersection, which is why dynamics that start over here could never go through to from one cone to the other because they would have to pass through a saddle point of the loss. But we see also there's loss saddle points in this downstream task as well.
But over there's two saddle points, but you can pass through because it's not like
Exactly. So in this case, actually, you can start with a positive A and move to a negative A.
So
And in fact, you're getting at a point which is that where we're going is that by just changing our initialization, we change this conserved quantity, and that conserved quantity has very fundamental constraints on the trajectory that the model can take in parameter space, which is going to lead to very interesting different behaviors in function space. We're going to get back to this rich, lazy story that we were talking about earlier.
just a question to understand the figure. So the white, blue, and red on the coloring, what is white? Is blue like worse than null kind of, or is that?
Yeah, this is probably a bad color map. Like white is like kind of, blue is the worst, is high loss, red is small loss.
And is
White is somewhere in the middle.
Should I think white is null?
White is kind of arbitrary, yeah, white,
Or it's just arbitrary?
yeah, it's just arbitrary for
Okay.
whatever color map I used, yeah.
Okay.
Okay. But I'm going to try to stay high level here. So I know this is a lot, and there is some high level intuition I'm trying to build. So in this paper, what we do is we say, okay, well, let's assume X transpose X is whitened, and this is a huge limitation of our analysis, but because now essentially all initializations will converge to the same solution. There's one OLS solution. But really what we're going to look at is the trajectory it takes to get there. When we do this, we find that actually we can solve the dynamics on those hyperboloids exactly by kind of this coupled Bernoulli and Riccati ODE, which really represents what we're doing is we're looking at kind of the angle between the parameters W and the solution and the norm of these parameters. So this is kind of a quantity that's invariant to the symmetry and a quantity that's very natural to the task. But there's some intuition that comes from this that I'm going to try to, once we have our ODEs that give our solution, we can now look at the dynamics of the kernel. And what we'll find is that when delta is very large, when we're in this two-sheeted setting, essentially what happens is there's very little movement in the kernel. And as I make delta larger and larger, the kernel moves less and less. And one way to actually intuit this is that as I move up this gray hyperbola, I notice that the gray and the red hyperbola are actually kind of converging to each other. Meaning as I move up, making delta larger, I'm actually getting closer and closer to a minimum. So this lazy learning is kind of associated with being almost initialized very close to my solution, thus I don't move far in parameter space, and the kernel does not fall. When delta is 0, I get some kind of interesting behavior where if I started with delta 0 and small, I'd be very close to a saddle point, and I would see actually a very sharp change in the kernel before essentially it's saturating. And then when delta is very small and negative, I can have another behavior where again I can see kind of in the beginning not a lot of movement in the kernel followed by a lot of movement in the kernel. And again, this is actually associated with being close to a saddle point in the loss landscape. So kind of initializing close to these two saddle points here. So what's the high level takeaway from this? One way of kind of understanding this spectrum of feature learning based on how I initialize in parameter space is if I'm initializing either close to a minimum, I'm in lazy learning, I don't move far in parameter space, versus if I initialize very close to a saddle point, I have these long plateaus followed by drops, and during those drops, the kernel changes. So this is this kind of parameter space explanation of what's happening under the hood when we talk about how the initialization changes the degree of feature learning. And we can see this more generally in a lot of different analyses. So this is a nice paper that I like from 2022, where they study the dynamics of deep linear networks, where they initialize all of the parameters with some power law in terms of the width, and they take the width to infinity. And they notice that essentially, this is now in terms of gamma, but they basically notice that when my initialization variance is very large, I'm in this kernel regime, where my initialization is actually very close to a minimum and very far from a saddle point. And when my initialization is very small, I'm actually in this saddle to saddle is what they call it regime, where I initialize very close to a saddle and very far from a minimum, and the dynamics look like they go from one saddle point to another to another. And then there's this kind of balanced mean field limit in the middle, kind of mean field approximately, where I'm initializing kind of equidistant between minima and saddle points.
So here when you say close and far from, you're literally measuring the distance from the closest minima and saddle in L2 distance.
Yeah, so that's what this paper does, is they look at this parameterization and they literally show that the L2 distance between your initialization and a minimum is shrinking as you are making the variance larger and vice versa for the saddle point.
L2 in parameter spaces.
L2 in parameter space.
And that's the closest minima and the closest saddle. So
Yes.
the math goes.
Yeah, closest minima, closest saddle. It's very kind of easy to see it here. As you shrink the variance of your initialization, you're going to the origin.
Sure.
If my parameters were all 0, you can't leave the origin. In the other sense, it's a little bit more difficult. There's some, you have to also control to make sure the variance doesn't explode and whatnot, but you kind of can get at that as well. And so again, what's the high level picture that I'm trying to paint here is we want to understand deep learning. To understand deep learning, we really need to understand this feature learning regime. And feature learning really is a spectrum. And one way to think about that spectrum is how close I am to a minimum and how close I am to a saddle. And so what they conjecture is that, look, this regime and this regime are quite well studied, but we should be studying this regime, this extreme feature learning regime. And they conjecture that in this vanishing limit, gradient descent visits kind of a sequence of saddles, in this case, each corresponding to a linear map of increasing rank. before reaching a sparse global minimum. And they kind of show pictures like this in their paper where you see these plateaus followed by drops, plateaus followed by drops. But this picture can be found in a bunch of other papers that we'll get to probably potentially at the end of this talk. So yeah, these kind of pictures, it should be reminiscent of that first experiment I showed where we have plateaus followed by drop. Okay, again, this is like a tour of analysis of all different flavors up for this one minimal model. I want to now point to a kind of an analysis technique I first learned from Natty's work, which is now instead of looking at the dynamics of parameter space, A and W, let's look at the dynamics of their product, beta. And so we'll call this kind of a function space perspective. Remember again, understanding dynamics in deep learning is all about understanding dynamics in different spaces. Parameter space, function space, performance space. We just talked about the relationship between parameter space and performance. Now I'm going to talk about the relationship between function space and performance. Interestingly, what you can do is, again, using that conserved quantity, you can find this kind of self-consistent ODE for the dynamics of beta in terms of the gradient of the loss with respect to beta. And one way to interpret this is that this, quite horrible-looking matrix in front is like a preconditioner that depended on both beta, so it's actually evolving through training, and my initialization, delta. And this preconditioning matrix is actually the same matrix that defines the kernel. So if this matrix is changing, my kernel is changing. But you might also be able to see that kind of this is alluding to this matrix is also going to change the dynamics I take in parameter space. So a strength of this analysis is that this holds when X transpose X is low rank. This is something we couldn't do in the parameter space analysis. And I'll kind of get back to that in a second. But let's see if we can get the same picture about how delta changes kind of the degree of feature learning in the same way we found previously. So when delta is very large and positive, we'll find that M is kind of converging to an identity matrix. And the trajectory you take in function space, here I'm just showing the level sets of the loss, is literally just the same as you would take in linear regression. When delta is 0, this matrix M has this identity plus this like rank 1 perturbation that depends on beta. And what you have here is that if you initialize very small, what will happen is you get this kind of behavior of silent alignment termed in previous literature, if you're familiar with it, where essentially that rank 1 piece evolves very quickly, changing your kernel before you then fit the task. And so you get kind of a slightly different dynamics in parameter space. And then again, when delta is very small, then negative, now M actually only is highlighting that rank 1 piece. And what happens is in the beginning, the dynamics look like projected gradient descent, where they're just going in the direction of their initialization before suddenly there's kind of a change in that M matrix, allowing it to sweep around and find the solution.
So how can we, I'm trying to match what you said to that.
Yeah, how can we see it up here?
No, how can we see it? The algebra you see, how do you see it in your figure actually?
Okay, so if M here is this rank, imagine it's just this rank 1, this constraint, then wherever I initialize defines a projection, a direction. I then project the gradient in that direction, and I can only continue to move in that direction.
Well, why is that the direction of initialization is what I'm trying to understand your figure.
Here? Oh, yeah. I don't think there's axes here, but it's here. This point is 0. The origin is not centered. The origin is like here.
Okay,
so it's kind of a weird figure.
Okay,
yeah.
but basically I draw a line from the origin to where I started, and I just continue
And
going.
I can't leave that line.
Okay.
Yeah.
When you write uppercase X, how do you arrange data as columns or as rows?
Sorry, say that again. When X.
Or capital X.
Oh, yeah. So this NTK should be.
Data.
It should be data by data. So then this in here is N. Does that make sense?
There was one where
I might need to think about. No, this should be D by D in the middle. So then this should be D by N. Yeah, so it's N by N on the outside because it's a kernel.
Which means
so
they're
rows. Yeah. So yeah, the kernel is like each element of this kernel is the inner product and the feature map between 2 points in your data set. So it's M by N, and then this M is preconditioning beta, so it's D by D. Okay, and one nice interpretation that you can then do from this perspective is now that we allow X transpose X to be low rank, we can ask this question that we couldn't ask before, which is, now among the many possible interpolating solutions, which one do you converge to? This is this very like rich implicit bias kind of perspective on things. We can actually, via a very similar analysis in this previous paper, we can derive kind of the same quantity. The only difference is we can allow for delta to be negative, but if you look at a high level, what you find is you find two terms in this implicit bias, one that kind of encourages minimum norm, which is rich, and one that's kind of trying to preserve this initial direction, beta 0, which is lazy. So this idea of like kind of preserving direction versus kind of trying to find minimum norm, there's kind of another way and perspective that I actually kind of like more that you can come from this, which is that what we're really doing by changing delta is we're changing the relative speed of the directional dynamics of beta compared to the radial dynamics of beta. And so this is actually a perspective that I think is the high level takeaway from this literature as a different kind of a function space perspective of the feature learning regime. The idea here is that in lazy learning, you kind of don't change your direction and you just try to fit using the directions you already have. So you have kind of fast radial directions, fast norm, but slow directions, slow directional dynamics. While in this rich regime, what you have is very slow norm radial dynamics, but very fast directional dynamics. You kind of have this behavior of aligning before you do anything in the problem. I also think there's kind of natural intuition between these two. You can kind of imagine that when you're on a saddle point, it's quite easy to kind of wrap around on the level sets of a saddle point before you fall off the saddle point, allowing you time to kind of figure out what's the best direction for me to go. Well, when you're close to a minimum, it's like you can't really change your direction. There's a lot of kind of force pulling you towards the minimum. Again, this perspective can also be observed in the literature, this idea of like kind of how in the small scale initializations we have, what we're really doing is we're kind of changing the speed. By changing the initialization scale, we're changing the relative speed of radial dynamics versus directional dynamics. This is a paper from 2018 that looked at ReLU networks, changing the initialization where input is scalar, output is scalar. And there's just 5 data points shared across these different plots. These are different initialization scales. And what they saw is that with higher variance, the solution it finds is kind of this messy, noisy, fit to the data. Well, as I make the initialization scale smaller, and in fact underneath some threshold, they find that all solutions the network ends up finding is this like linear interpolation between those 5 data points. So they made this note, this empirical observation that the discontinuities in the ReLU move while the training loss stays approximately constant. They kind of align with each other before they even do anything. So many subsequent studies have kind of used this behavior of distinct alignment and fitting phases at small scale initializations. And so now let's just kind of go back to this picture that I started with. I hope that I would be able to explain this to give some visual intuition between what I mean by the difference between kind of lazy learning and feature learning. In lazy learning, what we find is that there's kind of no movement in the directions. Maybe I should first just describe what we're looking at. We're looking at a ReLU network that takes input in 2D and output in 1D. And these blue and red regions represent kind of the sparsity activation patterns. So red means there's an odd number of ReLU neurons on, blue is an even number of on. So a ReLU network is really a piecewise linear map. So these are these little different linear pieces. And what we find is that in the kind of the kernel regime, what you see is that the network doesn't change the activation patterns, it just kind of fits up and down to fit the data. While in the lazy or in the feature learning regime, you see this initial phase where all the red and blue pieces are kind of aligning to some structure in the data, followed by some fitting. So yeah, this perspective of kind of just moving back a slide, the goal of this first talk was to kind of say, okay, we know feature learning happens, we know it depends on the initialization scale. This is a toggle I can use to either turn it up or turn it down. And I want to give some intuition of like what's driving that process. Why does that matter? And I kind of gave 2 explanations, one from parameter space and one from function space. So in the parameter space, it's really about the difference between being close to a minimum or close to a saddle. In function space, it's about the relative speed of direction versus norm. Okay. This is a good point to just stop. We still have about 15 minutes, but I think there was a lot of information, and I know that.
Maybe 10 minutes would be.
Okay, so 10 minutes. All right. So any kind of high-level questions? I don't expect anyone to follow all the details. I just want people to kind of really take home this idea that where you initialize in parameter space fundamentally changes your dynamics in function space and can either turn on or off feature learning. And I gave kind of explanations for that based on the loss landscape and this radial dynamics. Okay, you had your question.
Simple question. Shouldn't the dynamics also depend on the learning rate?
Yes, absolutely. Yeah, so in all of this analysis, I am using gradient flow. And all of this analysis is based on gradient flow, but one thing you can clearly tell is that in these extreme regimes where I'm changing delta, I need to be changing the learning rate accordingly. Otherwise, I will be stuck on a saddle or I will blow up in this, extreme lazy regime. So yes, the learning rate is fundamentally related to the initialization. So you can actually get all of this analysis by just playing with the learning rate and keeping the initialization effects. It's like a dual perspective.
Can you give some intuition why large scale in dish tends to be a local minimum? Why is that?
Yeah, it's not honestly in some sense very intuitive at first, but it depends on the problem. But imagine you have a really expressive network, and at initialization, it has essentially that network has access to all of these different kind of representations of the data, and you make this initialization really high variance. It gets all these very different initialization, very different kind of representations of the data, and what it can do is it can just kind of re-weight these representations by small amounts, and it can lead to very large changes in the output. So that's like kind of intuitively why it happens. I agree it's not the most intuitive, but let me try to rephrase exactly what I just said. At high variance, when your initialization is very large, small changes in parameters lead to large changes in the output. So if your network is very expressive and has all these different representations of the data, just small changes in the parameters can kind of re-weight these representations to kind of interpolate whatever data it has access to. So that's kind of the intuition.
So from practitioner's perspective, when I think of a feature, I think of a direction, not really how big that direction has in terms of magnitude. Because in the end,
yes,
my decision is just whether it's across a certain threshold. So
yeah,
it's not clear to me why a bigger scale makes your feature richer. It shouldn't matter.
No, it doesn't mean the feature is richer. It means that you don't need to change those directions in order to fit your data. You can just kind of re-weight all these different directions. That's the key idea, right? The difference is let's just take your saying, practitioner, I think of directions as features. Directions may be in parameter space, directions may be in some activation space. The idea here is that with large scale initializations, I don't need to change the directions. I don't need to change anything about the directions. I can just kind of re-weight them. And by re-weighting them, I can kind of get whatever I want in their sum. I can interpolate my data through just re-weighting. While at small scales, I can't just re-weight. I need to somehow align things and then grow. Yeah. Do you have, yeah.
I think you also need to add some additional assumptions about large initialization, because otherwise your initial distance towards the target function is also huge, right? That's much larger than the initial distance when you have zero initialization. When you have large initializations, right? You kind of need this assumption like zero output initialization.
Yes. In the Shazad paper, you need to assume that the functional input-output map stays zero.
But without that,
Otherwise everything blows up.
Yeah.
But that's a kind of a nuanced point that. But yes.
I guess to a practitioner, that's probably
yes. This is maybe for a practitioner a good point is that in these analysis you need to, as you change your initialization variance, you need to make sure that the input-output map doesn't change. Otherwise, you're just moving it into a really unstable regime.
Okay.
Yeah. So you need, for example, maybe you blow up the variance of all your early layers and you keep the last layer 0, for example. That would work. That would create this behavior. If you blow up, if everything, or you have some sort of symmetry, I didn't mention this, but if we go all the way back to this first slide, you might notice that in these experiments, for every blue point, there's a red point right next to it. I do that because that is how I make sure the input-output map stays 0. I basically created some symmetry in my parameterization so that my function is still stable in some sense.
If you want, if you want to talk about at this point about 5 minutes.
Okay, so let's save the remaining. Oh yeah, you can't speed through these slides. Let's go just to the second part of the talk, and I'm just going to kind of give the really high level. So, the second part of the talk is okay. We spent a lot of time talking about how initialization determines the degree of feature learning, and this relationship between saddle dynamics versus kind of kernel lazy learning. I really now want to study the mechanisms of this saddle process. What I mean there is kind of a simple idea. If we have this stepwise behavior, I want to try to in my loss, I want to try to like predict the levels of these steps and the times of those steps in the loss behavior. Or another way of saying this, that's kind of the parameter space perspective. Another way of saying this in more function space is I really want to understand why did my network kind of align to these specific directions? Like what about the data? What aspects of the data itself are the networks aligning to? So yeah, this paper we kind of conjecture we construct a framework that could just potentially describe this process in simple networks. And the key idea is that what we're saying is that gradient descent or gradient flow, let's take the learning rate out of the equation, just talk about the initialization. That as I take the initialization to the origin, gradient flow is actually converging to a discrete process where it's alternating between some sort of maximization and then a quick minimization phase. So I'm not going to go through the framework, but I'm happy to talk about this after or potentially Friday at a journal club. But essentially, we construct kind of a framework for a general 2-layer network like this. We show that this framework can capture existing analysis in the literature, kind of unifying it, and then we show in a very specific setting of modular addition how it can kind of predict behavior that is observed in practice, but didn't have a good explanation for prior to this. So I'm going to skip the kind of motivation and just give you the form of the algorithm, basically, the framework. The idea is that essentially along each of these plateaus in the loss, which is basically escaping a saddle, what's happening is there's an implicit optimization process driving the dynamics. This maximization process is basically maximize some correlation function subject to a norm constraint. And in the case, for example, of a linear network, what this correlation function is basically a bilinear product. This literally is like a Rayleigh quotient problem. Like maximize some sort of correlation with some representation of the data, but you can't change your norm. In doing so, you're going to align to like eigenvectors or singular vectors. Eventually, something changes. I won't talk about exactly what happens, but there's a transition where you jump out of this phase and into a new phase. And in this new phase, it's now a minimization phase, but over a smaller set of parameters. And so you kind of alternate between this process of maximizing, minimizing. After the minimization phase, there's a new function, and now things maximize again, and you alternate back and forth. So as I just kind of alluded to, in the case of a linear network, this maximization phase literally is like maximizing a bilinear product subject to a norm constraint, and you get eigenvectors. And the minimization phase is fitting the singular value. So the result is that in these kind of 2-layer linear networks, what you are learning is kind of you're iteratively or sequentially learning a singular value decomposition of your data, of your input-output map. So this saddle-to-saddle process is like an iterative SVD. And in fact, there's a paper that explains this exact idea. They call this greedy low-rank learning, and they propose this algorithm explaining it. And their algorithm really is this process. In this beginning, you iteratively construct a matrix factorization where you take a top eigenvector of essentially a residual, and this is this maximization. Then using that eigenvector, you minimize the loss, and this is this minimization, and then you kind of iterate between this, slowly building up a low rank factorization. We study another paper that does this for diagonal linear networks. Again, in this analysis actually comes from a very different perspective, but in fact, if you look at the algorithm they propose, you can actually find that this phase here really is a maximization phase, and this phase, well, it says argmin, is a minimization phase. And it directly, so here is just some visualizations of these dynamics. This is maybe just look at the loss and ignore everything on the left. But this algorithm that they propose, and this is the kind of framework that we get. And last, I'm not gonna, again, I know I'm jumping through this, but I'll end in 1 minute. So those were two existing papers that in the literature, we say, look, they can all be unified through this like max-min alternating optimization. What about a setting that we don't know exactly the dynamics of? So what we do is we look at this interesting behavior of neural networks, two-layer neural networks trained to do modular addition. And it's found that two-layer neural networks, what they'll do is they'll actually learn essentially a discrete Fourier transform of their data. So essentially the neurons will specialize to single frequencies. So I'm showing here the points are actually the vector, the weights of a vector for a single neuron, and you see that these neurons have different frequencies. And what we find is that this maximization phase is actually, we find that the cosine waves with a single frequency are the unique maximizers of that maximization phase. And then minimization phase does something else. But the result is that what you end up finding is that the neural network, what it's doing is essentially learning a discrete Fourier transform, but one frequency at a time, just like in the singular value setting. So it's kind of very similar to this idea of like aligning to a top eigenvector and then fitting. Here it's aligning to a frequency and then fitting. Okay, so yeah, I think there's a lot of interesting directions to continue in this line, and this line of literature is all about trying to study that saddle-to-saddle process. But yeah, I'm happy to take questions after, and I'll be in room 423 the rest of the week. Thank you.
It was great to have lots of questions during the talk. If any additional questions, especially by people who did not yet ask questions, or did already ask questions. Yeah. Yes.
Do you also study the effect of, let's say, adding random noise or dropout to the dynamics, learning dynamics?
So in this literature, no. I definitely have had some work thinking about the effect of stochasticity. My intuition, or what I've found in kind of prior work, is that stochasticity, finite learning rates, these kind of things always kind of strengthen this rich behavior. They seem to always amplify this rich behavior that you can also just find from the initialization scale.
A very high level question, like how important do you think this initial direction for the the incremental neuron is? Do you think it's important to do this power iteration at origin to get a direction that is super important, or like if we just follow this strategy of each time you add a new neuron and then you train to bring like a local minima of this current rank or the current weights, and then you add a new neuron, even if it's randomly initialized, it's probably going to get some kind of cohort. The bias.
Yeah, so I think in a linear network, that would be perfectly fine. You just say, look, learn a low rank.
Yeah.
Yeah, and in that case, it doesn't really matter where you initialize that.
Okay.
But I think in more complex settings, I think it actually might matter significantly.
So you're suggesting you have some empirical evidence suggesting the initial.
No, I think it's clear why in a linear network you don't need to pick out a special direction for this process to work. But that in some sense is yeah, I think that's special to the linear setting. It would be a good question to ask if in the modular addition setting if that would work or not. I don't know actually. Yeah.
Okay.
Wait, one more question.
Do you have any ideas about what happens for 3 layers and 4 layers?
So the biggest limitation in this framework is that we're stuck to thinking about 2 layers. One idea I have that I think is one way to think about it is that most networks that we look at actually have residual streams where there's some encoder, residual stream, decoder, and you add 2-layer networks to that residual stream. And so one way to kind of think about how to go deeper is not 3-layer, but 4-layer, where it's really like kind of nested 2-layer networks. So that's one possible like analysis strategy that I could see working. But I think how to think about this in a deeper sense is the key question. Yeah.
Okay, let's thank Daniel again.